in this thesis, we have analyzed network problems, and we have used stable matchings to do this, to derive the solution. These stable matchings found in the class of cooperative games. We have derived new results on these matchings, particularly in terms of existence and control of the equilibrium, and we have designed new allocation mechanisms, improving the performance of existing systems. Particularly, we have focused on resource allocation systems, or associations, and resource allocation. In this thesis, I'll show you two of the main contributions, as I've already said. The first one is about the Wi-Fi association in Wi-Fi networks. This is to say, between access points and users, we want to connect them with each other in order to reduce the impact of the anomaly, which is a drawback of the protocol. The objective is to improve the quality of service to the users. The second main contribution is the design of a new stable task allocation mechanism in schedule-constrained crowdsourcing marketplaces. We have also two other contributions. The first one is about how to enumerate the set of core stable structures, and the second one is about analyzing concavity conditions for the existence of core stability in generalized alpha-fair-based systems, but I'll present the first two in this PhD defense. So the first main question may be, why do we use stable matchings to tackle these problems? And there are three motivations. The first is that it is the natural tool that has been designed to tackle assignment problems in competitive settings in two-sided marketplaces where some resources are allocated among the agents. The second main also reason is that the equilibrium concepts, which are called stabilities here, are particularly relevant with respect to the problems that we consider, because they embed some properties that we want to use. In fact, as an example, in the Wi-Fi association problem, so users' devices are connected to the access points, using the core stability of matchings, let the agents match with each other, connect with each other, but let them also fight against the negative side effects by respecting their individual preferences. The third reason is that it has been successfully used in economics, and that computer science and electrical engineering communities have started to explore these games to see what is their propensity in solving network problems. What can we extract from this, both in terms of complexity or in terms of equilibrium properties that may solve the network problems. So first, a few words about these matching games. They have been developed for the analysis of two-sided markets, particularly two-sided platforms, matchmaking mechanisms on marketplaces. The objective, the aim is quite classical, as in non-cooperative or other cooperative games. First, define equilibriums, the right equilibriums that correspond to the existing systems and give good properties with respect to the agent's incentives, and show their existence. Also analyze the strategic incentives of the agents in manipulating the systems, how can they introduce bias in the allocation mechanism. And the third also, the third point is that matching games are also focused on the design of allocation mechanisms, matching mechanisms, for two reasons. First, to show the existence of this equilibrium. The second reason is knowing that there exists equilibrium, how to converge to this equilibrium. The impact has been quite huge, particularly in economy, because Nobel Prize has been given in 2012 to Alvin Ross and Shapley for their contributions in the design of matchmaking mechanism, resource allocation system, and there are some very well-known examples of problems that are mainly theoretical problems, or examples that have been used in the literature, or other problems that have been actually considered to design real system applications. So, the first well-known problem dates back to 1962, and this is called the stable marriage problem. So we just take some men and women, men have preferences over the woman, and the woman have preferences over the men. And one is looking for the marriage between these men and women such that no one wants to divorce. So the stability here is the fact that no single agent wants either to leave its mate or match with another partner. This is the marriage problem, and this has triggered a huge literature and a set of other examples that scientists have an interest in. So the second one is the college admission. This is just a more complex setting that allows for one woman, which is now a college, to be assigned many students. This is a many-to-one matching as opposite to one-to-one matching or stable marriages. And the third setting, well-known setting, is called the firms and workers problem. And in this case, firms are looking for hiring workers. and they may have preferences over the group of workers working for them, but the idea is that in this case, the workers are paid by the firms as an exchange, as a result of the tasks that they process in the firms. So, a few words about some basic elements and main results or challenges. In the two-sided market that we are looking at, the agents, whatever on one side or the other, emit preferences over the other side. It may be over individuals, may have preferences over men. It may be over groups, so a college may have preferences over groups of students. And it may be also preferences over matchings. The rest, what happens in the rest of the network or the marketplace has an impact on me and on my preferences. So this is for the preferences of the agents participating in the marketplace. The second point is the stability, because these are the equilibrium concepts that are considered in stable matching and that have been shown to be relevant with respect to such marketplaces. These are cooperative equilibrium concepts, and we particularly focus in this thesis on the pairwise stability, which is the stability of the stable marriages, or the core stability, which is nothing else than an extension, a generalization of this pairwise stability to groups, so a robustness to groups. The most fundamental result that dates back to Gale and Shapley's contribution in 1962 is the fact that in the stable marriage problem, which is this basic problem here, with preferences over individuals, stable marriages always exist. And that's a very strong result because there is not necessarily an intuition between this systematic existence. The main challenges are when the preferences are emitted over groups, so colleges have preferences over groups, or firms have preferences over groups of workers, or as a worker I have a preference over who are my colleagues when I am hired by another firm. And in this case, there are main drawbacks are that we cannot guarantee the existence of equilibrium in this case, so it's the existence of stable matchings. And assumptions have to be done, have to be found on the individual preferences. And an alternative, if such assumptions cannot be satisfied, is to consider alternative solution concepts that fits either more to the problem that we are facing, or that allows for weaker assumptions on the individual preferences. So one of the most challenging problems is to deal with matching with complementarities and peer effects. So as a college, I can see complementarities among the students that I want to hire, or peer effects. As a student, I care about which friends will be hired with me in the same class. So these are group effects. I have preferences over the groups I can take part in, and in this case, the existence is not guaranteed. The assumptions, as I've just said, have to be made on the preferences to show the existence of equilibrium. And as a particular assumptions that are very well known, there is the responsiveness, the substitutability, or the pairwise alignment. And the pairwise alignment is a very recent assumption on the preferences, and it mainly asks that any pair of agents should agree on the ranking of the coalitions they can both take part in. So if you and I belong to two coalitions, and we can both take part in these two coalitions, we rank these coalitions the same. We do agree that one is better than the other. This dates back to 2012, so that's a fairly recent one, and we will be using these assumptions for the next results. One of the most important also algorithm when dealing with matching with complementarities and peer effects is an enumerating algorithm that enumerates the set of core stable structures if they exist, and if not, then it converges to a given equilibrium. Here you can see two examples of what happens when there are complementarities and peer effects. Let's consider a production line, and workers are working on the production line, and they are paid according to the overall amount that is produced by the firm. And so green workers are the fast ones, so they produce fastly, and a good amount is produced, so they are paid, let's say, well. And if I take just two of them and put others that produce slowly, they will slow down the whole production line, so they are kind of bottlenecks on the production line, and then the overall production will be less than before, and individually they will be paid less. So this is an example of a peer effect, a side effect that may arise in the firms. This was for matching games with complementarities and peer effects. There is a second trend and a development with respect to matchings that has been proposed. This is to say, let's introduce contracts as additional elements. And in this case, a matching is now a set of contracts, and each contract is defined by a pair of agents and additional terms. So an association is no more a binary relation, matched or not matched, but it's something that is more complicated, that it says who is matched to who, but what are the terms for the association. So this may be in terms of salary or execution constraints. And we can also consider externalities, so what happens in the rest of the network has an impact on me, on my preferences. And in this case, the substitutability is still one of the main assumptions in matching with contracts. So it essentially says that agents reject weakly more contracts when facing more opportunities. In this setting, agents' preferences are commonly formulated using choice functions. So there is an equivalent formulation between preferences and choice functions. And they are usually shown in the form of tables such as this one. The presentation of stable matching and the main elements of this theory that we will consider in the PhD defense is now over, so I'll turn to the first main contribution that we have obtained, which is called Cooperative Games and Cooperative Games Theoretic Analysis of Wi-Fi. The first idea is to focus now on Wi-Fi, see the drawbacks, and then see how we can solve these drawbacks using the Wi-Fi association, a well-designed Wi-Fi mechanism for the association. So, first, Wi-Fi is a well-known, fully distributed mechanism. Particularly, it's known in the name of multiple random access mechanism. This is to say that the agents or nodes that want to communicate with Wi-Fi actually attempt to transmit using the underlying random process. So this is a very well-known and studied mechanism. So to communicate with each other, they use the Wi-Fi protocol. And for the association between access points and Wi-Fi in an infrastructure mode, so between the users and the access points that are connected to the internet, we use association scheme. The most known of them is called the decentralized base radio signal strength indicator, but this is known as inefficient. This is the first drawback because it may lead to congestion and overloaded access points. The second drawback of Wi-Fi is that we find back this bottleneck effect that we have been talking about before in production lines. So bad agents, slow transmitting nodes, actually reduce the performance of good ones. They slow down the whole group they are connected in. So there is an example of what can happen in best RSSI. Bad users may be connected to an access point with only good users, so it will slow down the whole group. And in this case, what we want to achieve using game theory in a decentralized setting is to make these agents connected to this access point in order to allow for these good users not to be interfered or slowed down by this bad user. So these drawbacks are well known. This is not new. There have been solutions proposed in the literature for a few years. The first is to modify the protocol in itself, the communication protocol. The second one is the second kind of solutions are to modify the association scheme in a centralized way, optimizing some given metrics. Also, non-cooperative games have been used for the user base station selection problems, whatever in cellular networks or in Wi-Fi solutions. And matching games have been also recently used for base station selections or small cell association in networks. Nevertheless, given our objective, which is to say design a matching mechanism, reducing the impact of this drawback, this congestion and peer effects such as the Wi-Fi anomalies, so the fact that slow transmitting agents slow down the whole group, and given the fact that we ask for a distributed system with selfish users and access points, each trying to maximize their throughputs, that we want to take these group effects into account, this anomaly, and that we do not want to modify the MAC layer, so the communication system, the protocol in itself. None of these solutions that have been proposed allow to design such a matching mechanism. So let's now enter into more details the game theoretic modeling. The first is that we consider what we call an infrastructure mode. On one side, the access point is connected to the internet, and on the other side, we use these devices. So it may be laptops, it may be tablets, it may be smartphones. So this is the two-sided structure that we are looking at, as we can find in stable matchings. The network, so there are the nodes that take part in this network, and this network is defined by a state of nature that is the result of the spatial distribution of the agents in space, and also of their standard compatibility, because the user's devices may be various in terms of brands or individual performances, achievable performances. And the data rates also that result from the modulation and coding schemes that is actually a bilateral agreement between the nodes and the access points that define their transmission speeds. We make an assumption, which is to say, we assume that there is an orthogonal assignment of the frequency channels among the access points. So there are no interferences, and this actually, in terms of stable matchings, will means that there are no externalities among the groups that are formed. So when connecting with each other, the agents form coalitions. An access point connected to this flatplot is an example of coalition. This access point connected to a tablet and a smartphone is another example of coalition. These are the kind of groups that we are looking to form when using matching games. And in each of these groups, agents communicate with each other on the downlink from the access points to the user's devices, or in the uplink from the user's devices to the access points using the Wi-Fi. So by using the Wi-Fi in each group, the agents receive a throughput, which is an expected throughput, and that we can also call payoff. And the payoff is actually the gain theoretic term that is equivalently considered in these cases for the expected throughput. So here is an example of what numerically we are looking at. This is an example of deployment. In the middle, there are, so here, small red cycles that are the access points. The black dots numbered here are the user's devices, and the green, red, and black cycles show the data rate regions. So inside the green cycles, you have a high data rate because the result of all this spatial distribution and modulation and coding scheme gives you a high data rate. So one here, in this case, we are looking for the associations with good properties in terms of minimizing the anomaly and the pure effects, associating the mobile devices black dots to small red cycles access points. Our first result is that when looking at such Wi-Fi systems and Wi-Fi communication protocol, given a coalition where the agents use Wi-Fi to communicate, the throughput allocation can actually be modeled as a Nash bargaining over the total throughput of the coalition. This was our first result, and this is very interesting because this means that even though it was not designed to be cooperative, the expected performances of the Wi-Fi protocol achieve a fairness scheme that is very well known in game theory and that dates back to the 1950s. So when receiving an expected throughput, a payoff, when I take part in a coalition, and since there are many coalitions, I can rank them according to this throughput. So I may have preferences about the connectivity groups I can take part in. This is actually what makes our problem fit in the firms and workers model. So I can belong, as a user device, I can belong to many groups, and I can rank them according to the expected throughput payoff that I receive in each group. And this is the same for the access points. I can, as an access point, I can rank the connectivity groups I can take part in. Using this, well, the fact that Wi-Fi induces is actually a Nash bargaining, and the fact that we are looking at a two-sided structure that falls in the scope of stable matchings, we can use Pitch's result that dates back to 2012 and which shows the existence of core stable matchings. So there exist stable matchings in this case in our problem, in our Wi-Fi association. And the core stability is very interesting because it lets the agents form groups with each other, but let them also fight against the negative effects such as congestion and such as the anomaly. But the problem is that when using this equilibrium concept and using an algorithm that converges to the equilibrium, we obtain one-to-one associations. We obtain stable marriages. So these are stable, but the drawback is that many users are left unassociated. So in this setting, so which is nothing else than the deployment scenario that I've shown before, the access points are connected with their best users' devices. And we are facing the problem of unemployment, in this case, a kind of unemployment. And the question is now, can we control the agent's incentive? Can we move the core from one set of matching, so one-to-one matchings, to another set of matchings, so many-to-one matchings that would leave less users as unassociated? And actually, to do this, we have designed a mechanism But the constraint was we do not change the communication protocol. We do not want to change the way the agents communicate with each other. We will rely on a modification that will come on the top of the communication protocol. This is a three-steps mechanism that we have been designing. The first step is called load balancing, the second step is called control, and the third step is actually a core stable matching mechanism. The aim of the first step is to define for each access point a number of users' devices it should be connected to at equilibrium. So this is a kind of objective that, that has to be achieved, or that the equilibrium should be as close as possible. So for each access point, the equilibrium should be such that it should be connected, the access point should be connected to its a number of users' devices that are defined for each access point using this load balancing scheme. This is a very generic scheme that may be based either on statistics or on the state of the system instantaneously. We have kept it general. Once knowing for each access point the number of connections that has to be achieved at equilibrium, the second point is how to make this achieved, how to make the core move to this equilibrium matching with the right properties in terms of number of connections, and this is the control step. This is the aim of the control step, which will create the right permutation in the agents, whatever access points or users' devices, and create the right permutations in their preferences so that we will move the core from one set of matchings to another set.